Hello everybody and welcome to another Advent of Code video, this time with day 15. Let's try to catch up a little bit with the pace of the event overall. So today we'll be solving some kind of beacon exclusion zone. Alright, so we have some sensors that have been built to locate lost elves. And the sensors are not very powerful. The handheld device that we have indicates that we are close enough to the source of the distress signal to use them. Alright. So once a sensor finds a spot that it thinks will give you a good reading, it will attach itself to hard surface and begin monitoring for the nearest signal source beacon. Sensors and beacons always exist at integer coordinates, so we'll be using points in a two-dimensional grid here. Each sensor knows its own position and it can determine the position of a beacon precisely. However, sensors can only lock onto the one beacon closest to the sensor as measured by the Manhattan distance. So that's distance, I think, like the street-based distance. So this basically sum of the absolute differences. Not diagonally distance, but the distance equal to the vertical plus horizontal distance. So it's basically just a difference between the point values. And there's never a tie between where two beacons are the same distance to a sensor. Okay, that's quite important. So there is always a difference between distances. Okay, so we get as an input a list of sensor readings where we know where the sensor is, and we know where the closest beacon is. So I will copy this as an input file for the simple example. And we consider the sensor at 218. The closest to it is minus 215. So 218. Yeah, so this is the sensor, and the closest beacon is at minus 215. This one. So that's the closest one. For the sensor at 916, so x916, the closest is 1016, right next to it. So each sensor only identifies the closest beacon, and if a sensor detects a beacon, you know there are no other beacons that close or closer to that sensor. But there could still be beacons that happen not to be the closest beacon to any sensor. So it means that there could be other beacons which were not detected by any sensor. So 87, what is that? Sensor at 87, yes, this one will detect 210, this one. So yeah, all these other positions are guaranteed not to contain any other beacon, and this means also equal distances because it has to be unique. So our goal is to determine where the beacon is not. So that's interesting thing to think about this way. So for now, so we will be keeping things simple by counting the positions where beacon cannot possibly be along a single row. So if we have row 10, So there are 26 positions where a beacon cannot be present. Okay. That's pretty interesting. So how to think about this problem efficiently? Let's see. I have a whiteboard prepared here, so what we can do is to draft it a little bit to see what we need to do. So if we know there is a sensor and its closest beacon is here, you know that there is gonna be nothing in this radius anywhere. So if you're going along a row, how do we know which positions cannot contain a beacon? What is the minimum and maximum? Where is the minimum, maximum y and x coordinate? That's weird. Oh, we need to determine where it cannot be. So yeah, right. So we need to determine which positions are too close to a sensor. So for each sensor and x coordinate, we can figure out which are the positions which are not allowed for that sensor. We can put those in a hash set of positions, and then do this calculation for all the sensors, basically figuring out which range of coordinates is allowed, which is not allowed, and then the union of all those options will determine to us the resulting number of disallowed coordinates. Yes, that makes sense, although we might not want to go through all the positions one by one, otherwise it would be quite inefficient, because these are quite big numbers to go through. Like it's millions, so in millions, so it wouldn't be something that a computer wouldn't be able to handle. But if we know the Manhattan distance is basically x difference. It's like a difference of x in absolute coordinate, absolute value of difference of x plus y absolute difference. So that's the Manhattan distance. And when we know that the points we're looking for are on one single axis, so we know that y is a constant thing, and we know the sensor y, then the difference between those two will be constant, right? So the difference between, so we know that the difference here is sy minus y. So this is a constant thing. And we know what's the maximum distance. So that's the beacon distance. So distance of beacon is dB. So we are searching for everything that has the difference, the absolute value is smaller or equal to distance of beacon minus y difference in absolute value. And because this is a absolute value, it has two different solutions. So xy less than db or less than db minus absolute of difference, or minus it's yeah, minus for the negative, so db so like this it should be is that the correct? So I have not solved inequality equations inequalities for a long time, so I'm not sure. So it should be, so the solutions are minus either the same or minus the value. So if it's negative, it's gonna be, yeah. So basically searching for those cases where this holds true, and so we can find the intervals. So if we can find the intervals of some x1 to x2 which are not allowed, then we can do some kind of union between those intervals, or actually we can union those intervals to get the real intervals, and then find the size of the total. So we'll do a sum of all the intervals that of xy, x1, x2, which cannot contain a beacon. Okay, so let's try to implement some part of it, so we can see if this works or not in an actual real scenario. So I will take the sample input as source for now, and I will try to implement this. So let's do, I will use point as a list, so it will be storing sensor and beacon as a pair, or let's make it nicer. Let's create a record beacon reading, which will have point sensor and points beacon, and we will use our useful tools library for this. And what I will do also is to have a public and distance point b. So we'll have a useful method that will give us the Manhattan distance, and this is actually what Copilot has suggested here. So the absolute value of the differences between of the coordinates. So that's good. So we have the record, and we will be reading those inputs. So lines, right, and for each. And now let's parse it somehow. So, oh, right. So let's go like this. So we will split the line. Yeah, let's see. We could use a regular expression maybe, just to make it simpler. Okay, let's just do regex. Let's do a regex to be fun. All right, so we have the string here. We'll do, we will want x equals, okay, equals sign. Right, we'll match this and then either a this way, single character, and I want it to be want to match numbers here, so 0 to 9. Yes, this way. And I want to do this anywhere. Yeah, and also minus. And also the end of line, which is what? How to mark the end of line? Oh gosh. End of string. Yes, it's this one. This way. Okay, so group 1, 2, -2, and 15. Yeah, that's good. So this should be the regex that we need. And we'll be matching on that, so. And we'll parse those values, so values, and so we'll have a sensor being point, values 0, values 1, and beacon will be 2 and 3. Good. So this will give us the values, and then we will add this to a list, or and we'll have beacon reading. So like this. So if I'm not wrong, which can definitely be the case, this should give us the proper input reading. So let's just put a breakpoint here, run it against the input to see if I'm still making any sense or not. Right, what do we have? We have 14 readings, 14 lines. Let's see, the 14th one. It's 21, 15, 3, 21, 15, 3. It makes sense. Okay, so that seems quite good. So now let's continue by implementing the logic itself. So I will have a okay, intervals, range. I think there is a range struct now which can be used for this purpose. I think it is. That one is built into C#, and we can use it because it's yeah, int, index start and end. So hopefully this should be fine for our purposes. Hopefully it handles also minus, but in case not, we will just adjust as necessary. So now for each of the readings, we will calculate the exclusion zone. So almost. So sensor. Okay. So sensor. Okay. Like this. And the beacon distance is then. That's the beacon distance. Okay, and the target line diff. So let's create a constant target y, which will be equal to the target line. In this case, in the simple sample, it's 10. So we will be doing the difference between reading right, beacon distance. No, what was it? So we know the distance. Yeah, sensor y and y, right? Y minus target y, absolute difference, of course, and then this will give us so xdiff limit is math. So this target. So this this is the absolute value of the x difference. So the maximum value of the x difference. So the disallowed x values are basically, so it's so we have so xdiff is x diff is sensor x minus target x of the target, an absolute value. Yes. So this is the on the left side. So you need to know which points are at most of this distance from the x. Okay, so the interval is then reading sensor x minus x diff limit and sensor x plus x diff limit. If I'm not mistaken, that's that gives us the excluded interval. So I'll mark it like this. Although I'm not really sure, it's actually index. So wait, let's make it like this. Instead of the built-in feature, we'll use this as more descriptive. So this way. So now what we'll do is when we have all the intervals, we'll sort them by the x coordinates. So let's do can we do this? All right. And now just so we sort them in a way. So now that we will have them sorted, we need to find the unique intervals, so to speak. So let's see. There was actually a better way to do it. I mean, there was you can put the intervals in a tree and create some kind of a binary tree where you continue splitting the intervals. So I'm not sure if that's the approach that's needed here. However, there is really just a very small amount of sensors there. So what we can do is to actually what we can do is to go through all the intervals in a n by n manner and find overlaps and just keep the overlap in one of the intervals and break down those which are overlapping. So let's do it this way. Or maybe you could just count the size of all the intervals and then discard the duplicates. So if we count the overlap multiple times, we'll discard it. So if okay, if we discard the overlap of multiple intervals, okay, let's just draft it. So let's suppose we have multiple intervals like this. So there is one from 0 to 5. Second is from 1 to 2. Third is from 0 to 4. If we count all of them, it will be, the total will be 5. Well, it's inclusive, so 6 plus 2 plus 5. So the total will be 13. But what we need here is to discard the duplicates. So the proper number should be 6. And now if I go like this, so I can let's count. If I count the first one, and now I remove that interval from all the subsequent ones, then I know that I will have no duplicates, and then I can continue the same process by removing duplicates from here and from here. So yeah, n by n, which is not a problem with this little numbers, this small amount of numbers, and it makes all the sense. So while there is an interval to check for, we will do the following. In the end, what we will do, we'll swap okay, like this. We'll just create a new array, a new list for it. And now we'll take the first interval and we'll now find the duplicates in the rest. So we'll go to the others and check for duplicates. So total exclusion. And we always include it. So total exclusion plus equals first interval first interval minx plus 1 for the because the interval it's not exclusive, so it includes the last cell of the interval. And now we'll remove the duplicates. So if there is an overlap, so what are the options? So either there is no overlap, so if oh, interesting. Intersection. Huh. But I don't need intersection here. So what I basically want is to take the part before the start, after, and inner. So if I can't interval okay. Because it's sorted, it should be unique. Or not, it cannot, it doesn't have to be unique, but it should be from the last, for the minimum x coordinate. So yeah, if the second interval starts before the first interval ends, then there is an overlap. That makes sense. Yes, that must be it. So if it doesn't, there is no overlap, we can just add it, and that is not needed. So we'll just add the second interval as is to the solution. But otherwise, we will have to add a modified version of it without the overlap. So what we will do is if first interval max x is less than second interval max x, so if there is any unique part of the second interval available, we will add it. So this is basically here, so we can do modified intervals, add new, and now it's gonna be first interval max x plus 1 to second interval max x. Yeah, so we'll add the unique part of that interval into the modified intervals. We add it, and then we start again for the second interval and so on. In the end, we should have 0 intervals left, and in that moment we can write the result. Minus 21 is pretty low. So that's there is some problem there. Let's see. What we can do is first check if this makes any sense. It might not. So the intervals. Let's see the intervals. So 3, 2, 1. So let's see. Right. This is a kind of a good thing to note, that we are thinking that we are working with the idea that the intervals are always sort it internally. So our x. So let's fix that now. So we have this, and what I will do is min x will be math min first x, second x, and the same for max. Okay. So this way, the interval itself will be sorted in a sense. So now we should have meaningful ones. 1, 3, 40, 4, 5, yeah, it all looks fine. Now, when I run the sort, it should be sorted, but it's not, because I'm comparing something that is completely meaningless, because I used E1 and E2. So now the intervals should be sorted. Yes, they are. And now this algorithm might work. Let's see. 27. 27? Why 27? There's just one more than we would want. Right. Why is there one more? Huh. That's interesting. That's very interesting. Let's run it and see. So this is -2, -2 to 2. So 1 to 2, so that's 5. Next one should be 3 to 3. So yes. 24 should be the one that's last. Okay, now this is the one where we made a mistake, so. Huh, interesting. So seems like we're counting something twice. For some reason. Troubles. So we have 4, 14, 19. F19 there. So the new intervals will be 17, 18. Next up should be 20. Okay, 21. Then we have 19, 20, 21, 23. So what we should get from this is 21, 21. 19 to 22, so that's 4, And now I have total exclusion of 23. So that's already wrong. Why is it wrong? Right, because we have 24 minus 2 plus 1, so 27, but there is a beacon there on that line already. Ah, right. So we have to exclude the beacons that are on that line. Right, of course, that's true. So, because on the position where the beacon is, there it cannot be either. So for each var reading, so for each reading we also add if no, right, that's wrong, because we were counting that beacon there. Oh. It's basically when there is a beacon, it's counted as a position where it is, even though another one cannot be there, but it's a matter of how you count it. So, so in this case, we'll need to exclude the beacon itself. Thinking whether it might happen, and it might probably happen, that some of those sensors are not even relevant to us, because they will never, their exclusion zone will never reach the difference, right? So if it's equal, less than or equal to 0, we skip it completely. And what we need is to break down the interval like this. Right, we just need to add the number of beacons that are on that line. It makes sense. So, right, so for each reading and readings, if reading beacon y equals target y, we'll just do total exclusion, decrement the total exclusion, because there is a beacon there. So now this should be, whoa, okay, interesting. So what happened? wrong there. I made this change, but xdiff limit, can it be like this? I think that change was sensible. 24. Stuff's happening here. Right, because we cannot count. We have to count unique beacons here. So we count this one 3 times. Why doesn't this work? So, if the distance to the nearest beacon if that is less than 0, then it should be safe to skip, because otherwise number doesn't make sense. But okay, maybe I'm missing here something. I got confused there. So let's keep it like this, because it seems to work, but I will try to figure out why it's not the way I think. So we're going to create a hash set. Let's do this immediately here. Now it should get us the right number, 26. And I can test it on the big input, but I'm still not sure about that problem that we have there. Right. Let's see. Ah, too high. Okay. So this is not yet completely right. Because it's true that if we have this sensor which detects this as the closest one, it cannot ever influence this line at all. But we are kind of counting it. So what's happening there? That must be the problem. So let's see. So let's check which is the one that is very far away. 218. So yes, this one is an example of this. It does not influence the 10th line at all. There's no, it doesn't cause any exclusion, I think. Or let's see if there is another one. 916. Yes, this one will not cause any exclusion. So 916. So for this one, beacon. Right, I need to test it on the small input. So for the second one, the distance is 1. Target line difference is 6. So, the diff limit is too big. So it will never reach the difference that we need. So this doesn't make any sense. It does not even cover the difference. So if it's less than 0, we shouldn't add it. Yes, that seems to be reasonable, but it does not work properly as we get 21, which is completely wrong. So why is that? So we have intervals 1 to 3. Okay. So there is no 1, 2, 3. So there's no minus. So we need to figure out what's happening with this sensor on position 11. Sensor at 11. Which one is it? Okay, locals. We will have sensor at 11. Okay, so the beacon distance for this one is 3. Target line difference is 1. And xdiff is... Oh, right. I swapped the condition here. So it must be greater or equal than 0, not the other way around. Of course. And now, 26. Now it seems to be correct. So let's put this to test against the big input. Let's see. This is a lower number, definitely. So let's see if it's even correct. Oh, it's still high. Okay. It's too high. So there must be still something wrong with the logic. So I'm thinking trying to replace all the ints with longs, which sometimes helps, but I'm... Boo! Right. But I'm guessing it's not... Okay, I need to just do it. Okay, let's do point. But this is not gonna be the problem. It's not gonna be a problem, I'm pretty sure. Come on. What is it? Huh? Where is it? Ah, here. So now this can be an int. What was my previous guess? Probably the same. It's most... Ah, okay. I'm not checking for the right line, of course. That's quite important. Right, so let's return this to how it was before. Because that's a pretty significant catch, because the sample input is checking on line 10, but in this case we're checking on a completely different line. and that will make all the difference. So 15. That's a much lower number. All right, good. Good. So that's the first part solved, and now let's continue to the other part. So we are the distress signal is coming from a beacon nearby. Four million is the maximum x and y coordinate, and 0 is the lowest. We need to determine its tuning frequency, which can be found by multiplying the x coordinate by 4 million and then adding the y coordinate. So there's just a single position that can have a beacon. Well, essentially, now instead of doing the search for forbidden coordinates, we need for forbidden coordinates for one single line. We will be trying to do that for the 4 million y coordinates and 4 million x coordinates. Like, we can modify the existing code to work for multiple different y coordinates. That's not gonna be as efficient, but it's gonna be easier than writing the whole thing in a kind of 2D manner, I guess. So we were just trying to find the first available position. Okay. All right. So this is no longer relevant. Delete all the readings and we'll make a method that will find available position given a long y coordinate. Okay. While. While we cannot find available position, we will increase the target there, and the method itself will be checking if we can find any available position on that in that space. So we will again read all the readings, find the distance to the target y, add it at the interval, which should be, oh, you can use ints, it's fine. So we will be adding that, and now sorting, and then we will be doing the comparison. So we'll be trying to find the first available position that's available. Okay, so we no longer need to calculate the total exclusion. Just need to find if what position is available. So if the min x of the intervals is higher than 0, and we return, then the result is let's do it like this. Return a point. Try find available position. Sort. Like this. And okay, let's see. I'm considering how to keep track of the start of the line. So okay, if min x is greater than 0, then we know that we can place a beacon at the beginning. It's kind of weird. Okay, return. Yeah, I'm not really sure about this one, but let's see it if it makes sense when we have it. So return true. But if not, then let's mark it like this, and then we will go through all the intervals. We'll see if we can, if this y is available. Do it like this. So if our min available x overlaps with the interval, then we have to move it some to forward. If it's greater than the min available x, we have the solution, so we write the result. Right, so we can use it in general manner. So min available x equals 0, and we can do it like this. Yeah. So it's greater than we have the solution, and we set it to min available x target y and return true. Otherwise, we move it to the end of the interval, unless the interval is shorter than the one that we had previously, but it shouldn't matter to the max of the interval. So math max x and min available x. So we don't move it back if we find a shorter interval. This way we should be able to get the actual value there. So if in the end, if it's less than yeah. So nice. Less than or equals the size. Then we return new result this way. Else result default and return false. Okay. So for the simple sample input, we should get 1411, and that should give us this number. Let's move it up from here. So console right line result x times. Why do I get it here? Okay, let's result. So it's times this plus result y. So let's try to run it against the simple input. And of course we need to limit this in this case by 20 because they said the input is just 20 by 20. 1411. That seems to be correct. So let's try. Let's try. I'll use this. And I will run it against the big input. And fingers crossed. This takes a bit longer, yes. And we have a result. Although it's gonna be a big number, so probably overflow. Oh, maybe it didn't, but we'll see. No. It's too low, yeah, so we overflown. We need to do so it's gonna be a big number, so a big number plus equals result y. This way we should be able to calculate it without overflow. Yeah, it's a big number, but it might be correct one. Ah. 1 second, wait. All right, good. This one was a tough one. Okay, so that's day 15 solved. And we have 3 more to go to catch up with the pace of advent of code. But I'm pretty happy about this one. This one was a tough one, especially to figure out the right approach to the problem, and also to notice all the edge cases and all the weird specificalities of all those positioning and so on. So this one was a tough one, and it's only gonna get worse. So yeah, it's gonna be fun to see the next days. So I will push my changes so you can check the code at your leisure. And you can subscribe if you want to get notified about new videos. But in the meantime, have a good one, and see you in the next video. Bye bye.